Sure that actually started. 10. All right, so let's go over this homework assignment. I did have you omit number 9 and 10, and later on I went back and we actually did talk about that sort of kind of indirectly, but we'll still go over it today. Okay, so we'll just go through these in order and we'll do 9 and 10 as we hit them. Number 1, true or false? This value has the same value in both unsigned and 2's complement form. Well, let's look at this in unsigned and 2's complement. Okay, so is this the unsigned version of that number? What number is this in decimal? So 1s, 2s, 4s, 8s, 16s, 32s, 64. So it's 64 plus 32 is 96, plus 8 is 104, or 107. All right, so is this the unsigned representation of this number? All right, what's the 2's complement representation of that number? Well, how do I do 2's complement? Flip all the bits, right? So this would be 1, 0, 0, 1, 0, 1, 0, 0. And then we add 1 to that.
But that's not the same. Wait.
Yeah, it's negative 107 now.
Yeah, wouldn't that be negative 107 now?
Okay. Well, the question says, true or false, this number has the same value in both unsigned and 2's complement form. Okay, so now you said you add to a 0 in front of it, right? So when you took this value, actually let's just start from scratch. Before you took the 2's complement here, you wanted to do a 0 onto the front, and then you flip the bits. What's the 2's complement of this? What's this question actually asking? It says, are they the same number? Are they the same decimal number? Are they the same binary number? Do they have the same bits? How do I take the 2's complement of this? Make it a quiz? So let's go back to what I had just a second ago. I had this guy. So you told me this is negative 107, right? Why is it negative? Is that bit?
Yeah.
Oh, is this the correct 2's complement of this number?
Yeah.
Are they the same value?
Yeah.
So what's the answer to this question? They're not the same value. Question here, though, is did I take the correct 2's complement? If this is an unsigned value, does that mean it's positive? Well, by definition, if it's unsigned, do we assume it to be positive? Do we write a plus in front of the number 75?
No.
We just say 75, and we assume that's positive 75. We only say something, we only put a sign if it's a negative number. How would I represent this number in its 2's complement form? By definition, isn't the 2's complement of this number the negative of this number? That's what it means, right? Isn't that what 2's complement means? So here's a follow-up question. Can this ever be true? Can any number, can I put any number in here that has the same value in both unsigned and 2's complement form? 0? Okay. Anything else? The only number you can think of? What about a 1? 1 wouldn't be, right? Okay, so this is false. Not the same. Number 2, true or false? The single precision floating point number, this scary guy, is negative. That's the question it's asking. Now, it's a big, long number, but we actually only need to consider one part of it, right? This is that IEEE standard. So if we look back at the slide set here, we get to our IEEE standard. That very first bit is the sign bit. And if it's a 1, it's a negative number. If it's a 0, it's a positive number. So this guy has a 1 there. So, true or false? This precision floating point number is negative. Is that a true statement?
Yes.
That's true. Okay? That's a negative number. Make sense? So this kind of threw you a curveball. Looks really scary, but all you had to do is look at that 1 bit. Number 3, what is the lowest possible value for an 8-bit signed number? What's the smallest value that an 8-bit signed number can hold? Negative 120. I hear 127, I hear 128. Which is it? It's negative 128. Why is that? So really what we're saying here is this. We're saying that a signed number, 8-bit signed number in Java, this is a byte data type, correct? Can hold plus or minus 2 to the 7th power. Plus or minus 2 to the 7th power. So if it's signed, we're going to be able to hold the smallest number is this guy. That is, the sign bit is the 1. I'm going to put a space after the sign bit. Okay? So the smallest number is what? What's the biggest number? Is that the biggest number? Well, for the 7 bits. For the 7 bits. Is this also the biggest number? So it's the same ones, but a different sign bit? Well, why is one of these 127 and another one is 128? What makes this guy down here 128? Oh, we convert these to decimal. This is the 1's place, the 2's place, the 4's place, 8's, 16's, 32's, 64's. Add all those up, what do we get? 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. That gets us 127. So this 7-bit number is 127. This 7-bit number is 127. Why is this one a negative 128? Well, we know it's negative because of the sign bit here, right? But why is it a 128? What do you think? Talked about this one too.
Because the 1 is 255 minus the 127.
Ah, this is a negative 255 minus, well, you say 255 minus the 127 or negative 255 plus the 127 gets as a negative 128. That makes sense? Because of the place that this is in. All right? Where this one doesn't have a scalar for that. So we wouldn't get that 256 number, 255 number. All right. So that is number 3. So lowest possible value for an 8-bit signed number. 2 answers you could have put in there. Actually, realistically, probably the answer that it's really asking for is 8 ones. Negative 127, or sorry, negative 128. But you could have also put in the decimal, negative 128. That's fine. Okay. What is the highest possible value for a 10-bit 2's complement binary number? So 10 bits. You did what?
I deleted number 4 off of my document when I was doing when I was going through and giving all the answers.
Okay,
Number 4 is no longer in my document.
Do you still have number 4?
I never did number 4 because it wasn't on my document.
Oh, the question wasn't.
Yeah, I deleted the question. Okay.
So there's a 10-bit number, right? 10-bit number. What's the highest possible value for a 10-bit 2's complement binary number? Well, highest possible value is going to need to be positive, right? Okay, so how do we solve this one?
First bit has to be 0.
Okay, first bit has to be a 0. So that guy right there is a requirement. 2's complement holds a sign. Okay, what else? Rest of them ones. Okay, what value is this?
511.
Positive 511. So that's plus or minus 2 to the 9th power. All right. Okay. So you could have written the binary version of this, or you could have written positive 511 for the highest possible value. Either one is fine. Make sense? Number 5, convert each of the following decimal values to 8-bit 2's complement binary. So let's do 54 first. It is a positive 54, correct? So there's 54. So convert each of these following decimal values to an 8-bit, I'm sorry, I said 2's complement. Where did I read that from? Oh, I'm sorry. Oh, we are on 5. Good. The 54s threw me off. I'm working on very little sleep. And by very little, I mean no sleep.
How much did you sleep?
I slept from about midnight until 1:50.
Don't let him handle any power.
All right. So in any case, this was a fair mistake because both of these have 54 at the beginning. This was an eye tracking problem. Convert each of the following decimal values to an 8-bit 2's complement binary. So we have positive 54. Okay, so this is the decimal number. I need to write positive 54 as a 2's complement value. How do I do that? Well, convert this to binary first. Okay. So what's the binary version of 54? That's 32 plus 8 is 40 plus 4 is 44 plus 2. Oh, I did forget 16. 32 plus 16. 32 plus 16 is 48. Okay. Plus 8 is too much. Plus 4 is 52. Plus 2 is 54. So that. Okay. Yeah, there's only 6 bits. We need to pad it out. And this is an 8-bit number. Okay, so that's the 8-bit equivalent of 54. And we need it to be a positive number. Is this the answer? Is that legally in 2's complement form? That is the positive version of 54. Make sense? Okay, next one. Negative 49. We're going to convert positive 49 to binary, then take the 2's complement of that to get us to a negative 49. Okay, so positive 49, that is a 32 plus a 16 plus 8, 4, 2, 1. Right? That's the right number? I need some confirmation here, people. I think that's the right number, correct? Okay. So, we're going to flip all these bits. So we have 1, 1, 0, 0, 1, 1, 1, 0. Then add 1 to that. Is that negative 49? I think it is.
Did you have to add a 0 to the front? At
Didn't
the
I?
beginning before you flip the bits?
Didn't I?
Oh,
No. No.
No, you don't need to in this.
It needs to be 8 bits.
So this is an 8-bit number. So this was our added 0. So that's negative 49. Okay, remember, 2's complement is the inverse of whatever the original value is. So we get the binary version of positive 49. 2's complement makes it a negative 49. Negative 128. That's 128, 64, 32, 16, 8, 4, 2, 1. So that's positive 128, correct? Flip all the bits on that one. What happens? 0. One, 2, 3, 4. And then add 1. So adding 1 to this guy. One plus 1 is 0, carry the 1. 1 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 plus 1 is 0, carry the 1. That. So this is our 2's complement version of negative 128. Okay, negative 66. At least we're getting easy numbers for me to convert to binary. Kind of. I'm pretty stoked about the 128. I followed that one. All right, so 66. We have 1 in the 64's place. 32, 16, 8, 4, 2. Right? Pad it with a 0. This is 1, 0, 1, 1, 1, 1, 0, 1. Negative 66. Oh, gotta add 1 to it. Sorry. So that's 0, carry the 1. That's 1. So that's the answer. 1, 0, 1, 1, 1, 1, 1, 0 for negative 66. Then we have negative 98. So we have 64 plus a 32, that's a 96. 16, 8, 4, 2, 1. Is that right? Is that positive 98? 1s, 2s, 4s, 8s, 16s, 32s, 64, 64 plus 32 is 96, plus 2 is 98. Good. I'm only sort of kidding when I say I need some confirmation. All right. Okay, but this is negative, so we need to take the 2's complement of it. So we have 1, 0, 0, 1, 1, 1, 0, 1. Add 1 to that. One plus 1 is 0, carry the 1. So now we drop down the 1. Then we have 3 more 1s. So this is our answer. Negative 98. 1, 0, 0, 1, 1, 1, 1, 0. Okay. That it for that question? All right, questions on that one? Number 6. B again. Negative 49? Did I mess up? I'm taking you think I did.
I just want to see how you did it again.
Okay, so this is 136. So that's the 36th place, 16s, 8s. So we're at 44. 4s. That's 49, right?
So why did you add 2 zeros?
To pad it out to 8 bits.
Right, but
1, 2, 3.
Can you go back to the question?
Yeah, the question says 8 bits, I think.
To convert it.
Convert each of the following decimal values to 8-bit 2's complement binary.
Does that mean you change it to 8 bits before you do the 2's complement or after you do the 2's complement?
Before, because I mean we're storing it. Think of this as being stored in an 8-bit register. So we're storing the number 49 in 8 bits, but we actually need to represent negative 49. So we're going to encode it in 2's complement format.
You do 2's complement with less than 8 bits and then just add zeros to make it 8 bits.
Mm-hmm.
Once you do it, then it's not the same number because 1 wouldn't be the first.
Mm-hmm. Yeah, so really think about it from a hardware perspective. If we were storing this value in a computer, we're going to store the 49, but since we need to store it as a signed number, we're going to encode this in 2's complement. So 2's complement of this, we flip all the bits, so that's... you got this. 1, 1, 0, 1, 0, 0, 1, 0. I think we just found out why I'm leveling slower. Then we're going to add 1 to this. That's a 1. That's a 1, 0, 0. That's a 1, 1, 1. So that's the answer. 1, 1, 0, 1, 0, 0, 1, 1. This is 49, right? 1s, 2s, 4s, 8s, 16s, 32s. 32 plus 8 is 40. Plus 4 is 44. Hold on. 1s, 2s, 4s, 8s, 16s, 32. So 32 plus 8 is 40. Plus 4 is 44. Oh, did I skip 16? Man, why am I? It's pretty bad. 32, 16, 8, 4, 2, 1. That. And 1, 1, 0, 0, 1, 1, 1, 0. Add 1 to it, so we get a 1, a 1, 1, 1, a 0, 0, 1, 1. So this guy, 1, 1, 0, 0, 1, 1, 1, 1. Is that better? So I would have encouraged you all to use your program that we wrote that converts binary to or decimal to binary, just so you don't have these mistakes that I'm.
So I know one of my programs had bug in it.
What's this?
I know one of my programs had bug in it.
All right.
Since mine to check it, but that'd be converter.
Yeah. So really, there's not a great excuse to have an error here. We're just trying to do it on the fly. The conversion down here to 2's complement is pretty easy. If it's had a negative number in the front, we encode it in 2's complement. If there's not, we don't. Make sense? All right, so that was, okay, so that's number 5. Number 6, convert each of the following 8-bit 2's complement binary numbers to decimal. All right, so our very first one is this guy. Something actually paste, is that the right number? I was kind of expecting to have to turn it into white text from black, but apparently it held the format. Okay, so first of all, is this a positive or a negative number? Negative number. So this guy's encoded in 2's complement, right? So what do we need to do? Okay, how do we decode it? Well, how did we encode it? Huh? Flip the bits and add 1. So how would we decode it? Flip the bits and add 1. What's 2's complement? 2's complement is the inverse of a number, right? So if we have, let's just use 56 as an example. If I take 56 and I take the 2's complement of it, I get a negative 56. If I take the 2's complement of that, I get a 56. Does that make sense? So 2's complement is the inverse of a number. So we can implement this through addition. So we already know this is a negative number. So we're going to go ahead and flip all the bits. That's 0, 1, 1, 0, 0, 0, 1, 0. All right. Then we're going to add 1 to that, which is just going to get us a 1 there, right? What's this value? This is the 1's place, the 2's place, 4's, 8's, 16's, 32's, 64's. So this is 96, 98, 99. So this is negative 99. Make sense? Okay. Out of curiosity, how many of you recognized that you could take the 2's complement of the 2's complement to get the original value? Oh. Never actually mentioned that in class. I mean, you probably could have tried to do subtraction and made it work. But if you noticed in class, we always tried to do subtraction through addition, right? But since we were only subtracting 1, you can sort of kind of make it probably work. But we can see it's not easy to do subtraction. But that concept, that trick of just taking the 2's complement of it again gets you your original value. Very interesting. Okay, so that was this one, this value, oh, because our original value had a 1 out front. So this was a negative number. Okay? This was the 2's complement representation of a negative number because it had a 1 there. So now we had to find out what was the original number. The number was a 99, and we know we'd throw the negative in front because it originally had a 1. Make sense? All right, so here's our new number. Positive or negative number? Positive number. So do we have to take the 2's complement of this to get it back? Oh, we can just convert this. So this is the 1's place, 2's, 4's, 8's, 16's. So this is 21. Positive 21. Make sense? All right, then this one. Positive or negative number? Negative. So we got to do the 2's complement thing, right? That's going to be 0, 0, 0, 1, 1, 0, 0, 1. Then we're going to add 1 to it. Which is going to get us a 0, carry the 1, a 1, a 0, a 1, a 1, all the rest zeros. So this is the 1's, 2's, 4's, 8's, 16's. So 16 plus 8 is 24, 26. So this is a negative 26. Is that right? Finally, this guy. Positive or negative number?
Positive.
Positive number because of the 0 here. So this is the 1's place. 2's, 4's, 8's, 16's, 32, 64. 64 plus 32 is 96. 104, 105. Positive 105. All right. Okay, so that's number 6. Questions on that one? Okay, so not too bad. Number 7, convert each of the following decimal values to 8-bit signed binary. All right, so we're doing the inverse of what we just did. So we got 54. I want to convert 54 to signed binary. Is this a positive or a negative number? Positive number. All right, so let's go ahead and so given that, do we need to turn it into a 2's complement? We don't have to encode it. It's positive, right? All right, so we're going to have 36 plus 16. Got the 16 that time, right? So we're at 52. 8, 4, 2, 1. Is that right? 1's, 2's, 4's, 8's, 16's, 32's. 32 plus 16 is 48. Yeah. Now we're right? Okay, good. I was testing you. I won't remember it. All right, so we don't need to take the 2's complement, so that's our answer. And it did say 8 bits, so the correct answer should have all 8 bits. If that's the only thing you miss on that one, I probably won't take points off, but it did ask for an 8-bit representation, so you should pad it out. All right. Negative 49. And really, had you done number 5 correctly, number 7 should actually be pretty easy, right? Aren't they kind of inverses of each other? So negative 49 We know it's going to be a negative number, so we're definitely going to have to encode it. So we're going to get 49 first. So that's 32 plus 16 is 48. 8, 4, 2, 1. Is that 49? 1s, 2s, 4s, 8s, 16s, 32. So that's 48 plus 1 is 49.
How do you know if it's in twos complements? If you're
Well,
basically reading it.
we're just looking at the, oh, I understand. You'll have to be told that the number that you're looking at is a signed number.
So if we have
That way you know the far left bit has meaning. If you're not told it's a signed number, you don't know whether to interpret the far left bit as a pad bit or a 1. See what I'm saying? Yeah, somebody's going to have to give you that information. That makes sense what he's asking? You know, if I just show you this number out of the blue, you have no way of knowing what I'm representing there. Because I haven't advertised that as whether it's a signed or an unsigned number.
That number wouldn't necessarily matter.
That particular number wouldn't, because if it's signed versus unsigned. But the point is, you don't know what it is. So this would matter. Right? That makes a difference. All right, so this is positive 49. Now I need to take the 2's complement of that, so we're going to flip all the bits. 1, 1, 0, 0, 1, 1, 1, 0. Add 1 to it, which gets us that 1. So this should be our answer. 1, 1, 0, 0, 1, 1, 1, 1. Right? Okay. Then we have negative 127. So that is going to be 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. We know it's a negative number, so we do need to take the 2's complement. So that's 1, bunch of zeros, like that. That's negative 127. 1, 6 zeros and a 1. And negative 66. That's going to be the 64s plus 32s, 16s, 8s, 4s, 2s, 1s. So is that a positive 66? 64s, this is 1s, 2s, 4s, 8s, 16s, 32s, 64. 64 plus 2 is 66. Flip the bits because it's a negative number, so we need to encode it. 1, 0, 1, 1, 1, 1, 0, 1. Add 1 to that. Get that as our final number. 1, 0, 1, 1, 1, 1, 1, 0. I think it's the right answer. I tried to do the math quick in my head, but I think I did it right. That's the number we had initially? No. 1, 0, 1, 1, 1, 1, 0, 1. That's the number we had initially. Add 1 to that. So that's going to be 0, carry the 1. 1, 1, 1, 1, 1, 0,
Wait, if
1.
you carried the 1, wouldn't it be?
The 1 would drop down right here. 1 plus 1 is 0,
Oh, yeah,
carry
yeah,
the 1.
Sorry, yeah.
Yep. So this is the number I had before, right? I think so. So this is the answer. I just tried to not show my work, and then I started doubting myself. But as usual, I got it correct. 50-50 at best. All right. So that's negative 66. Negative 98. That's going to be a 64 plus a 32. That's a 96, right? Plus a 16, 8, 4, 2, 1. Is that a positive 98? And we do need to encode that, so we'll flip all the bits. 1, 0, 0, 1, 1, 1, 0, 1. Add 1 to that, so we have 0. 1 plus 1 is 0, carry the 1. 1, 1, 1, 1, 0. That should be our final answer. 1, 0, 0, 1, 1, 1, 1, 0. All right. Number 7, convert each of the following decimal values to 8-bit. No, we just did that. Just did that. How long are you guys going to let me do that?
long as it took.
All right. I hate all of you. All right, number 8, convert each of the following 8-bit signed binary numbers to decimal. So this is kind of going along your question. They've informed us it's signed. All right. The book that I didn't make you buy. It's a really expensive book. It's like a $240 book. It's ridiculous.
Is that on Amazon?
What's this?
Is it that on Amazon?
It probably is. There's probably an old version of it or something. Book prices just got out of control. But as students, you just don't. I mean, you don't have a choice, right?
Oh, I got it on Amazon. I
Sort
spent
of.
$30 on all my books.
You can just pretend that you have the book.
Oh no, I get it. But you might put yourself at a disadvantage.
Yeah.
Yeah, I don't know. I've always been an advocate of, many of you might find alternate ways of getting the book. I would never encourage you to do that. But the point is, I think most of these classes, at least in computer science, there's so much documentation on the internet and stuff. Do you really need a $240 book? I could probably make an argument for a couple of books that it might be useful to have it on your shelf, but even any more, you'd rather have the ebook version. So, like the operating system class, having a copy of that Dinosaur operating systems book is probably something that should be in your library, but get an old Kindle version or something, or a PDF of an old version, kind of just make the decision that, if they had 4 versions ago for Kindle for $8, I'd buy it. But since they don't, they want to sell me the current version for $130 for an e-copy. You forced my hand. All right. So in any case, they is the book have told us that this guy is a signed binary number. So there's our first number. Already got it in there? No, I don't. There's a number. Okay, so we know this is going to be a negative number, correct? So we know that this guy is encoded. So the first thing we need to do is we need to decode it. And we decode it by flipping the bits and adding 1. 0, 1, 1, 0, 0, 0, 1, 0. Add 1. Here's our value. This is 1s, 2s, 4s, 8s, 16s, 32, 64. So this is 96, 98, 99. Negative 99. Okay, so that's what this first one is, negative 99. Second one is a positive number, so we don't need to decode it. This is the 1s, 2s, 4s, 8s, 16, so that's 24, 25, positive 25. Is that right? 1s, 2s, 4s, 8s, 16s, positive 21. I did fix it in my head the second time, so it's the race condition and you won. All right, so positive 21. This one. Encoded? It's encoded because we have a 1 out front. So we need to flip all the bits, add 1 to it, which gives us a Nah, I could have just done this. That's adding 1 to it, right? This is 1s, 2s, 4s, 8s, 16. So that's 16 plus 8 is 24, 26. So this is negative 26. Right? All right. Number 8 and number 6. Convert each of the following 8-bit 2's complement binary numbers to decimal. They've told us right off the bat these are all in 2's complement. Every one of them is in 2's complement. These, only some of them are actually in 2's complement. They've just told us these are signed. So some of them were not encoded already. These are all encoded.
Don't you do the same work for both problems? Because even if it was 0 at the beginning, you don't have to decode it. So both ways, you just do the same thing.
That's true.
The same numbers.
Yeah. But it is asking a different question. But you are right. You are right. The solution is going to be the same because you are a 2's complement number of a positive number by definition was not encoded. Just like these wouldn't be encoded either.
It's the same as questions 5 and 7.
Yeah.
The same.
Did I just do this one?
Yes.
So positive number, don't need to decode it. 1s, 2s, 4s, 8s, 16s, 32s, 64, so 96 plus 8 is 104, 105, positive 105. All right?
What did you get for A?
Oh, come on.
Didn't you get negative 99?
Yeah.
What did I get for A? Was it negative 99? That's what I got. Is that right? I think it's right. You want me to solve it again? Did you get a different value?
Yeah.
All right, hold on. Definitely encoded. So we need to flip all the bits. 0, 1, 1, 0, 0, 0, 1, 0. Add 1 to it. We have that. This is the 1's place, the 2's place. 8s. No, 1s, 2s, 4s, 8s, 16s, 32, 64, 96, 97, 98, 99. This is negative 99.
Okay.
See where you went wrong?
Nope.
Don't you have to add 1?
You did it.
I did.
I missed that.
Yeah, this is the ones I do it in my head when, wait, hold on, is that still the value? When I flip all the bits, so this is 0, 1, 1, 0, 0, 0, 1, 0. Since this has a 0 in it, I know I can just put a 1 there. Add 1 to it, and we're fine. But then I fake myself out, wondering if I actually screwed it up. All right. So you still don't see where you went wrong?
I'm trying to figure out because I took the sign bit off. And then I converted the rest of it, and then I added the sign.
But why would you take the sign bit off? Sign bit's part of the representation. Or you know that now.
Right.
All right. So you know what you did wrong.
Maybe? I'm confused.
Because this is encoded in 2's complement, this sign bit is part of the encoding. It's part of the value. It can't just be removed because it's not part of the actual value. You know, it is part of it. All right.
Wait, we're on B now.
No, we're not. We went back into that. All right. So now we're to the questions that you guys omitted, right? All right. So let's talk about these. So we're supposed to convert this binary-looking floating point number to its decimal equivalent. So we have a number that looks like that. Okay? Now, we talked about this when we did it in the slides. Actually, let's do a little bit bigger number. 132.123. I started off as pi, but I actually want more numbers in the front of the decimal point so you can see the idea here. So to the left of the decimal point, this is the 2 to the zeros place. This is the 10 to the zeros place. This is the 10 to the ones place. This is the 10 to the twos place. So that's 100 plus 30 plus 2. This is the 10 to the negative ones place, 10 to the negative twos place, 10 to the negative threes place. And if I can show you in, was it here? Yeah. So we looked at it from a decimal number perspective, how that works. So just like converting between all the different bases is the same regardless of what the base is, you just change, instead of 2 to the 0, you 10 to the 0, or you do 16 to the 0th power, something like that. So this was when we discussed that concept. So in this case, for this number up here, this is the 2 to the zeros place, 2 to the ones, 2 to the twos, 2 to the threes. This is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3, 2 to the negative 4, 2 to the negative 5, 2 to the negative 6, 2 to the negative 7. All right? What is 2 to the negative 1? Okay, it's 0.5. Why is it 0.5? 2 to the negative 1 is the same thing as saying 1 over 2 to the first power. Okay. So this is 1s, 2s, 4s, 8s. So that's 8 plus 4 is 12. So this would be 13 on the front. Correct? So we can do that math. We're used to doing that binary. All the positive 1 binaries, we're good with that. Right? So now we need to deal with what's after it. Okay? So this is 0 in the 2 to the negative 1's place. 0 in 2 to the negative 2. So we have 2 to the negative 3 plus 2 to the negative 4 plus 2 to the negative 6, 2 to the negative 7. All right, so we have to do that math. So 2 to the negative 3 is 1 over 2 to the third. So 2 to the third is 2 times 2 is 4 times 2 is 8. So 1/8. Okay, so this is 1/8 plus 2 to the negative 4s is 1/16 plus 2 to the negative 6 is 1/64 plus 1/128. All right. All right. So now 1 divided by 8 plus we have 1/16. 1/16 plus, what was my next one? 1/64. I hate you people. 1/8, 1/16, 1/64, 128. Aha! 1/64 plus 128. So 0.2109375. Let me copy it. Ha-ha! So this would be the answer. 13.2109375. Make sense how that worked? Remember, the question asked us to convert this binary representation. Now, technically, you could have argued that this isn't in binary. It just looks like it's in binary. Although I think in the book they actually had B's on there and I took that off. Or they had 2's on there and I took the 2's off. So you actually couldn't argue that from the book. You can argue that I made it an ambiguous by removing the 2.
Hey man, I'm just gonna make fun of something.
What did I do? Did I not remove it someplace else?
No, I was just gonna say that now binary has 1s and 0s and decimal points.
Well, it can. That's the point. It can. Binary isn't just a representation for whole numbers. It can represent floating points as well. As well. What's this? Oh, you're half asleep?
Well, yeah, I'm half asleep, but he said that you did that because of lack of
Then I'm half asleep. Actually, I don't feel that bad.
I don't feel that bad either.
Yeah, feel it.
I mean, I'm a little upset that you're so far ahead of me in leveling.
I have a really good attention span.
I know. Isn't my guy like way more geared than you too?
Yeah.
What's your eye level?
Not
No, I'm sure it's still.
like 40 less than yours.
And you're still not 570 now, right?
No, of course not.
It's not about the gear, it's about how you use it.
Not as bad as the operating system joke from yesterday. Did everybody in here hear about that? The operating systems class joke? Yeah, I had a slide. I can show you the slide real quick. That'll cheer us up if some of you are depressed about the homework. It was chapter 3, right? Yeah. So Tim over here was questioning whether or not I was the one who wrote the slide because it specifically has 4K child in a box right here.
And you have to execute it.
And then we execute the child.
Yeah.
That's right.
We broke a student.
we broke a student. Now, what's really funny is when I originally learned that stuff, I don't remember like thinking like that. Yeah.
Oh, yeah.
So I think like society is like broken. The fact that like literally 100% of us just went there. I mean, it's like depressing, isn't it?
Come on, this is supposed to cheer us up.
I mean, back then, you just couldn't look up things on the internet and find dirty things. Nowadays,
Well, we didn't have. You don't think we had the internet then?
no.
You didn't have Google. You could type in
Formats.
goats and just get all sorts of fun things. Type in 4K child.
We went outside until Nintendo came out. Then we stayed inside.
Oh, you're going outside and trying to look up something that.
Online gaming was make your friends come over. All right. So in any case, that's the answer to the first one. Second one. It's this guy right here. Same exact dealio. That value. Before the decimal point, this is the 1s, 2s, 4s, 8s, 16. So 16 plus 4 is 20, 21. 21 point. Then we're going to have 2 to the negative 1. So it's 1/2 plus 1/4 plus 1/8 plus 1/32. 1/2 plus 1/4 plus 1/8 plus 1/32. 0.09625. What's that number? Okay. 1/2, 1/4, 1/8, 1/32. Yep. That makes sense? How those work? So you lucked out there. It actually was Yenter's fault, and he's not even here today. He's have his sister's wedding or something. Yeah. I think we both know why I remember that. Now I'm not sure the recording knows. People, it sounded way worse than it actually is. Yeah. Last class, he told me he had to go to his sister's wedding, so I had a follow-up question.
Immediate.
Let your mind.
No
I just wanted to make sure it was an excused absence.
His sister.
Yeah, what the heck?
Look, college is important, people. All right, next one. Convert this value to the IEEE standard 754 for single precision floating point value. So we're going to go back to this dude. Nope, not that dude. That dude? Nope, not that dude. That dude. This dude. So we are inversing this guy down here. So we have 1 point whatever, blah, blah, blah. So the value we're starting off with here is this guy. Copy that. So we're on that slide there. So there's our value. All right. All right, so if we have a positive number here, this guy is the sign bit. So right off the bat, we're going to have that guy, right? Now, the exponent, this guy right here, E, is, well, whatever we have here is this value minus a 127. Okay? So let's go back here. Oh, why do I keep doing that? So we'll start building our answer. So we have the sign bit, which is going to be a, killing me. Okay, so in this case, the sign bit's going to be a 0 because it's a positive number. This is positive 1 point. It's not negative. So sign bit is going to be a 0 because it's a positive number in our example. Okay, then our example has a final E of 34. So that means when we took some value, subtracted 127 from it, we got a 34. So 127 plus 34 is equal to 161. Okay? So we know that the decimal version of E is 161. What's the binary version of that? That's 128 plus, not 64, plus 32, plus 32. So at that point we're at what? 160. So 32, 16, 8, 4, 2, 1. That? 101, 0, 0, 0, 0, 1. Is that 161 in binary? Ones, place, twos, fours, six, ones, twos, fours, eights, 16s, 32s, 128. So this is 128 plus 32 plus 1. 28 plus 32 plus 1. Is that 161? Ha! So E is that value. Okay? Then we have our fraction portion here. So this value 0, 1, 1, blah, blah, blah. 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1. That gets us to right here. So that's our fraction value, and then we pad it the rest of the way. So everything after this and what's that variable called? That's called F. So F is that. And how many bits should this be? How many? 23 bits? Do we put the zeros before or do we put the zeros after? Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Okay? So final answer is 0 followed by this followed by this. So 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Ah, feel good about it. Does that look right? So, not hard, just had to plug and chug it with the formula. What happened?
None.
Oh, did you?
Yeah.
SPD?
Yeah.
Good.
Oh, why do we need to go up to here?
Because if we look at the standard, I'll go one slide back from this. We have two standards. One of them has an 8-bit exponent and a 23-bit fraction. The other one has an 11-bit exponent and a 52-bit fraction. The one we're dealing with is going to be an 8-bit exponent. And actually, that's one thing we didn't double check here. Is our exponent 1, 2, 3, 4, 5, 6, 7, 8. We kind of lucked out just because of what the value was, because we didn't actually explicitly pad it to 8 bits. If this had been a smaller value, we would have had to make sure we put zeros in the front.
Could it be a smaller value? Because
Oh, it absolutely could be. But you still need to represent it as an 8-bit value because of the standard. The standard says the exponent is 8 bits.
I thought the exponent can't go below 0. Because it's minus 127, so you have to have at least 127. Right? Or can you get like a 63 minus 127 and have a negative exponent?
So let's say, no. I see what you're saying. Yeah, I think it will always come out to 8 bits.
Yeah, because you have to be.
It will. You're right. But if for some strange reason it didn't, we'd have to pad it. But in this case, it would be impossible for it not to. But to answer your question, that's why we had 23 bits, because that's what the standard says we need to have. So if we weren't representing enough bits, we need to just pad it out. All right? But we put the padding on the end because it's on the other side of the decimal place. Those are the least significant digits. Digits. What was digits from? Wasn't that from 470? Have you guys had that yet? No. We do a project on digits in 470. Big digits. You write a programming language that supports that. It's a nightmare. You're going to love it. Okay. So that one makes sense. But the standard's what tells us how many bits. But we did, as Jordan pointed out, Jordan, who's Jordan? At least I proved I know your name.
Sure.
We padded after the final bits because these are the least significant portion of the fraction. What comes after the decimal place. If we look up here, this digit right here is, well, this bit is less significant than this bit. It has a smaller portion of the value. So that's why we're padding on the opposite side than we usually do. Where if we're on the left-hand side of the decimal point, we usually pad binary numbers to the left because those are the more significant values. A 128 has a bigger impact on the number than a 64, than a 32, so on and so forth. All right. So that was 12, 13. Using hexadecimal arithmetic, add this guy. Who? No, I didn't. I just saw the standard. Okay. Oh, yeah. Okay. Binary equivalent. Yeah, we have time for that one. We got 3 minutes, right? so our sign is a 1. Next 8 bits is our exponent. Now let's go ahead and convert this. This is the 1s, the 2s, the 4s, 8, 16s, 32, 64s, 128, 133. It's positive 133. So 133 minus 127 is 6. So we're going to ultimately have an exponent of 6. All right, then the fraction portion is the rest. So this is 1, 2, 3, 4, 5, 6, 7, 8. So starting here. Good. Give us a nice size number. So we got that. So final answer is negative 1 point. This guy times 2 to the 6th. Look right? Yes. It's to be in the standard, the zeros are actually, yeah, the zeros required to be in the standard in this case.
Because you padded it on the other one. So
We padded it up to 23.
you can still pad it.
Yeah.
Question 11 doesn't have all the zeros on it.
Yeah, it's true. You don't need them. It's not wrong to have them. This is just a bunch of insignificant digits that multiply by 0. So it doesn't matter. Just like padding zeros to the left-hand side of any binary number doesn't change the value. All right. So let me at least start this one. So doing some hex math. There's that value. We're adding to it this value. Yep. What happened?
What's going on? I'm really confused. Hey now.
For A432. Did something funny happen? Or just the... Did I miss like textual phrasing? I don't like to miss that stuff. All right, so we'll start off here next time. We'll finish up this assignment and we'll start talking about logic gates. All right? If you struggle with the assignment, at least go back through and look at some of the things that you missed up to what we've talked about so far. I may or may not give a quiz on Tuesday dealing with something we've covered in the homework up to this point. Maybe a hint. I could see me maybe covering something like 9 or 10 on a quiz. Whoa. Okay.
Slow down.
I could see 9 or 10 being covered on a quiz. Not difficult, but something you just learned. All right? I'll see everybody on Tuesday.